All right, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Claudia Alexander, who's come up to us from Jet Propulsion Laboratory, where she's currently working on the Rosetta mission. Claudia did a bachelor's in science at UC Berkeley in geophysics, and then a master's at UCLA in geophysics and space physics. And then she did her PhD at University of Michigan in space plasma physics. Then she moved to back to the Bay Area and worked at USGS on topics of plate tectonics, and also worked across at NASA Ames and worked on the Galileo mission. She worked on Jovian moons, and then in 1986 moved down to JPL, where she currently is located. She worked on the plasma wave instrument, was eventually the project manager on the Galileo spacecraft mission, and her career interests have revolved around topics such as the evolution and interior physics of comets, Jupiter and its moons, and also the planet Venus, magnetospheres in general, and plate tectonics and space plasma, solar winds, and so on. So she has also, in addition to all this, published some children's books on Venus and mountains for grade 3 and grade 4 audiences as well. So today she's going to talk to us about the very recent success of the Rosetta mission. So please join me in welcoming Claudia.
Well, it's great to be back here in the Bay Area. I'm originally from the Bay Area, and I just am so pleased to always come back. I love coming back to the AGU every year because it's back in the Bay Area, and it's really a treat to be back here to see some of the people that I started my career with. You know, it's a real treat, and I just am pleased and really hope that you enjoy this talk. I'm here to talk about the International Rosetta mission, which just had its landing, and the orbiter mission continues. So let's play the first video, if I can get this.
When the Rosetta spacecraft set off for a rendezvous and landing on the distant comet 67P Churyumov-Gerasimenko.
Comets are really important. They're like a time capsule back to our past. They were formed just as the planets were formed in solar system formation.
We'd like to understand then, is that the original material that the solar system kind of went from something like that to water and oceans and palm trees and the like? How do we know what our original solar system was made out of? Does the comet really represent some of that original material? And it's so very different. How do we get, from there to where we are now?
Now I love this next one because we have this great animation, so I just have to use that to start off the talk. So here's where we are now after a 10-year journey. The European Space Agency launched our mission, and we had a launch delay. So originally we were supposed to be done by 2011 after having launched in 2003, and instead we launched in 2004. And here we are now. So a good 10 years in space, which is a really long time. We have no RTGs whatsoever, so we are a totally solar-powered spacecraft. And that meant that we had to go quiet. Basically, they turned the spacecraft off approximately here through the aphelion phase and turned it back on over here, and that made everybody very nervous, okay, because without even a beacon, okay? So next week, you're going to have an engineer who's going to come talk to you, and you should talk to him about some of these questions, like why did you do that, and what were you thinking, and so forth. So I'm not going to talk about that, but in January of this year, we had our first stroke of luck, which was when we turned on the spacecraft. It came on again, and we were able to find it. We were prepared to spend a week searching for it, and we were able to find it. Now, what I want to do in the next couple of slides is remind you what a comet is. Okay, a comet is basically a nice rock, an icy rock in space, although rock is maybe not the right term. As it comes around the sun, it begins to outgas, and it makes these beautiful tails, a dust tail and a gas and ion tail. And here's another example, the Chinese tapestry. You know, we have been fascinated by comets for thousands of years. And the most recent ISON, which turned out to be kind of a dud, but was very beautiful at about 5 AU, with the beautiful tail and the beautiful nuclei and coma, which is in the front. So the objective that the Europeans came up with back in the 80s, they kind of, as they tell me, they carved out comets as the thing they wanted to study in the solar system. Let NASA have the rest. And ESA, we want to do the comets, which are the original material, and we want to get some of that original material. So we want to send a spacecraft, and we want to send the instruments that are going to ingest some of that stuff and allow us to, you know, with a laboratory analysis, figure out what that stuff is. And that was kind of the genesis, following on from Giotto mission at Halley's Comet, the genesis of Rosetta. So let's go briefly over what is a comet made of. Frozen gases of assorted kinds. It turns out that before Rosetta, we had not actually measured anything very complex, even though on paper a comet ought to have, the coma should be filled with organic material, and that parent and daughter products of organic material should be there. But we never measured it up until, you know, from the ground. And then the solid material, and when I had my graphic artist prepare this drawing, basically, you know, I kept telling her, no, it's got to be more refined, more intimately mixed. Because at first, I think we thought that it was more like a meteorite with these big grains. And the more we start to study interplanetary dust particles and the like, the more we're starting to understand that probably the comet is a more very intimate mixture of the ice and refractory material. It's not even formed in terms of a mineral. It's a refractory material and with ginormous molecules, probably. But Rosetta's purpose is to go there and take the measurements that allow us to understand how this material is intimately mixed, if at all. And another thing that I want to point out on this diagram is that the surface is very dark. So it's very black, kind of like the black toner we used to use back in the day in our printer machines. So that's really dark, and I don't know of any I don't know of any ice mixture that is that dark. And one of the questions is, how do you get that kind of material? How do you get it as black as that? One of the things we hoped to do was to create a mass spectrometer that could basically, help us understand and separate out what was at mass 28 among other masses on the periodic table. So 28, in the past we'd gone to comets, and mass 28 is equivalent to CO and N2. And so we didn't have a unique measurement of both of those very fundamental properties of the ancient solar nebula. So one of the purposes of building one of the fanciest mass spectrometers ever, a state-of-the-art mass spectrometer, was to be able to separate those two fundamental particles among other particles on the periodic table. We want to understand how the comet works as a machine. And among those, among the properties that you need to know is the thermal, not only the radiation, the brightness temperature, but also how the heat transport within and sideways. And so we had a number of instruments whose purpose was to get the thermal conductivity by measuring the thermal gradient down below. And we had instruments on both the lander and the orbiter whose purpose is to help us determine some of those fundamental properties. We have a really wonderful experiment, one of my favorite ones on the lander, whose purpose is it's a tomography experiment, which is kind of like an ultrasound of the nucleus. So basically, if you have on the left here, at least my left, we've got a relatively uniform, although it's got pockets of stuff in there, and the radio waves penetrate, and by timing the radio wave getting back to the spacecraft, there's one receiver on the lander and one on the orbiter. They can reconstruct what's in the inside. If there's any sort of layers, like there's a crusty stuff on top and more poofy fairy castle style material underneath with maybe even more pockets of heterogeneous stuff, maybe more rocky stuff inside, that we would be able to begin to penetrate what was inside and understand what the content of this nucleus is. A very, very difficult experiment to pull off, however, if you have one of your radio receivers is moving. Right? Ideally, what you'd want to have is stationary radio receivers to try to get the content of what's inside. So ultimately, this is an incredibly difficult experiment to pull off in practice. One of the first things that that got our attention as soon as so I said that we turned the spacecraft off and then got lucky when we turned it back on and it came on. And very shortly thereafter, we recommissioned the spacecraft, recommissioned the instruments, and started watching, and one of the first things that happened was this wonderful outburst. And I have to admit that I was taken by surprise. Some of our scientists will tell you, oh, I was not taken by surprise. I of course knew that there would be outbursts well towards the orbit of Jupiter, well outside the orbit of 4AU. And I think we all kind of expected that, yeah, there are outbursts on comets. We see them on many comets, but I think if we would have expected to see one, we would have started watching earlier. This was, almost as soon as we turned the camera on the target, there it was. And and then after that bit of activity, the comet activity went down to normal. So we're still trying to, we still have to take the data that'll help us to understand what was the physics behind the outburst at that time. In this little movie, we have, it's kind of amusing. We thought that we would have a normal sized nucleus. And this is, of course, not to scale. The nucleus is a couple kilometers in size, and the spacecraft is not that large. But this is kind of how we envisioned looking down, doing the measurements over the surface. And this shape was created by doing all the light curves and so forth that we expect to do from the ground. And so even as soon as after that outburst, we still had in mind that we had a sort of normal-shaped nucleus body. And then when we got close enough to take the observations of the resolved observations of the nucleus, this is what we have. And so we don't know. I think it looks like the boot from Monopoly. But most people think it looks like a rubber duck. And so even though we have very technical names for the lobes, the major lobe, the minor lobe, and so forth, we still call it the head and the body of the duck and the neck. Okay, so this is a very interesting region. You can see cliffs, what look like cliffs, and then a very loosely constructed bit of terrain in this area here. And one of the first questions, of course, is, are these morphologically or chemically different from one another? Is it a true contact binary, or is this a single body that has a very unusual erosion pattern on it? Okay, let's see if that's on the next slide. It's coming up, okay, but it's a couple kilometers by 4 kilometers. So we began doing the temperature maps and so forth, and the shape models. So this is one of the first shape models with 5,000 facets and the temperature. So part of it is illuminated, but this is actually the northern summer. So a little bit later, this is going to be, this region that is illuminated now is going to be dark. And so what we have is, this part is where the neck is, where some of that loosely consolidated, what looks like loosely consolidated dirt is there in the sort of gravitational low, and also in what is going to end up being in a very cold part later on as we get closer to the sun. This was one of our first temperature maps, and let's see, this is a movie, if it works. Okay, yeah. So the surface temperature turned out to be a little bit warmer than expected, but not inconsistent with a dusty, something that's very dusty and insulated with dust. That is consistent with measurements such as these from the infrared instrument at different 1.4 and 5 micron wavelengths with the shape model rendering. And really, I do think that looks like the boot. I'm sorry. Okay, this is the boot. Okay. Here are the dimensions that I mentioned. So approximately 4 kilometers in one direction and approximately 2.8 in the other direction. You may have seen on the web various artists taking it and plopping it down in Los Angeles, for example, or plopping it down in the University of Bern. You know, wherever you live, you can take this and plop it down and give an idea of approximately the scale. So this scale here fits approximately across metropolitan Los Angeles, okay? And this dimension rises about 10, the tallest building in LA times 10. So that gives you an idea of what the scale is of this object. Here is a wonderful shot of its level of activity already. You can see what look like collimated jets. One of my favorite things to ask people is, how do you know if you fly through this that you're in a jet or not? It seems to me that it looks obvious to your eye that there's a density enhancement in some of these places, but I'm not convinced it'll be obvious if you fly through what the actual enhancement is. So we will find out, because we're going to try to fly through that at some point. But right now, the neck seems to be the most active, or at least early on, the neck was the most active. And we wanted to get the lander down before the whole thing became active. Here's another wonderful close-up, and again, you know, you're looking at what looks like a very dust-covered surface with boulders. How do you get boulders on an airless body like a comet? I think that's still a very, very interesting question. You can see the size scale goes down. Even from boulders the size of houses to much smaller scales, and then smaller scales still on these so-called plains. So this is very interesting with very different slopes, and then these roundish-looking features that are filled in to various degrees on the surface. So we're going to land on that. And they laughed. The guy who's coming next week, ask him about this picture, because the guy who commissioned this picture went around and asked about 60 different people what the expectations were, and he put this together based on their expectations. But you can see cliffs in the background, and we laughed. Ah ha ha ha! There won't be any cliffs. You know, it'll mostly be pretty flat. And obviously, we hope that it will be flat, because the lander isn't really built to land on a boulder the size of a house. And there might be some vents, and we would hope that the comet wasn't active, because the vent could literally blow the lander away. depending on how much mass is coming out and the amount of drag that there might be. So we had some preconceived notions, and then when we actually started planning for the landing, it was you know, a very interesting trial to try to figure out where is best. Now, one of the features of being in orbit around a comet is that you can't really be in orbit around a comet. The three-body problem means that there's only a certain amount of time where you have bound orbits are possible. So the engineers, the navigators, came up with what they call isocahedral orbits, which are kind of square orbits with points on them, or in this case, what we had was sort of triangular-shaped orbits. Later on, when we get probably past mid-January, we will not be able to do bound orbits at all. So we will have hover and swoop kind of trajectories where we'll get to one of those points and we can stay there and let the comet turn underneath us. And then we can arrange a flyby, a close or a far flyby. And part of what we're doing right now is arguing, you know, where do we want to go? Do we want to go down to 15 kilometers and face those jets, those with chunks of stuff coming out? Do we want to be 100 kilometers away and not have that much signal to noise, but give our remote sensing instruments a chance to do some good observing of the comet as it starts to come alive? So those are some of the arguments we're having now. At the time of orbit insertion, which was August, we basically used that triangulation to approach the comet, and then we began to do our bound orbits around the terminator. But you can see here that we still had, when we planned this, we still had this idea that it was a normal-shaped object. We had to do the gravity characterization, the shape characterization. All of those things had to be done in a very short amount of time, approximately 45 days, in order to tell the landing people where the best landing site would be. So here we had the green dots are kind of representative. I told you that one of my favorite experiments was the tomography experiment, and they had to have regions of the comet that this radio signal could pass through and be accessible to the orbiter. So that ruled out some, so we couldn't land in the neck region, for example. And there are other reasons not to land in the neck region. There also was that we needed to have solar illumination. We needed also to have diurnal variation, or at least the scientists wanted diurnal variation to, again, understanding the thermal conductivity of this body and how it works as a machine was part of what we were attempting to learn. So that, you can see here that among our favorite spots were the head of the duck, or the minor lobe, which also has an official Egyptian name, which I'm not going to try to pronounce. I was not in favor of the Egyptian terminology, I'll be honest, but I lost that argument. And here's a neat lander deployment, which was, again, how we thought it would go. It's kind of amusing to look at how we thought it would go. So again, we kind of have this lunar, it looks like the lunar Maria down below, without those gigantic boulders and without the sort of dusty component. We were going to have 3 legs that had screws in them. When they touched down, they were supposed to screw the lander in, and we had harpoons that were supposed to also deploy immediately. And then on the very top is a retro rocket here that was supposed to fire and hold the lander down, okay? And I don't know how many people have written to me. I have a guy from Africa wrote to me and said, it's Newton's third law. It's, you know, it's action-reaction. Didn't you know that when you fired the harpoons that was going to cause the lander to bounce? I mean, I can't believe that you people at JPL couldn't have figured that out. So here's another one. So this is with the real landing site with the cliffs, okay? Once, you know, we had sort of blocked out where we couldn't go what sites were really bad. We did not have a site that was really good. And this site, we needed to have slopes that were not more than 30 degrees. The lander could not handle that. And let's look at this again. This ended up being the landing site that was chosen as the best of the worst options. And, you know, it doesn't look so good. You know, there's some really spectacular cliffs, finally. And I actually should figure that out for this. But it's a not insignificant vertical relief on this. It's the kind of thing you would not want to hit. And it's possible that we may have hit something. So, you know, what we didn't want to have happen, have it land on some sort of slope that we would end up tumbling down, land in some sort of incredibly active area that had more force than the lander, that would end up having us not be 3-axis stabilized. Again, you know, a cliff, and then sinking down. And this was my principal concern, was how deep were we going to sink in this dusty, insulating stuff? Okay, and how deep is that stuff? To me, one of the reasons to send Rosetta is to try to figure out, for a small body that has very little gravity like a comet, what is the depth of this stuff, and is there a crust? Back in the 90s, we had what was called the Cosy Experiment, which was in Europe, they would lay some ice down slowly on a cold finger, and they would bombard it with energetic particles, and a crust would form that was of a relative strength of 4 to 5 megapascals in strength. And then underneath, you would have this fluffy ice, so it's almost like an Oreo cookie. You know, you have the crusty black stuff on top, and inside the pristine, icy stuff. And when they launched the Deep Impact on July 4th, I think it was 2005, to Comet Tempel 1, the idea was to try to test this notion of a crust that would, if you blew a hole in it, would you expose this fresh icy material, and that you would evacuate and have brand new pristine stuff. And it did not work out that way. So we began to rethink the physics of comets and sort of got away from this idea of a dusty insulating layer over some sort of crusty material that was, again, over more of the pristine stuff. And just going back to the landing site, we had 5 sites. 2 of them were on the head of the duck. And where's site J was this one is a little bit hard to see because this is, again, the head of the duck, and this is the body of the duck. And site J was the one that was chosen, and we ended up more over here in the end. So this was an early shot of site B, which actually is really beautiful. It's kind of like, let's land right here, and what is this stuff? Because maybe we could observe that stuff. Well, there are these boulders that are ginormous here, so we would want to avoid that. And because the navigation was so uncertain, the navigation error ellipse was enormous. So that kind of ruled out, and then there was some thermal anomalies, I think, with this particular site that ended up ruling that out. And site J, even though the terrain doesn't look so good on that movie that I showed you, this was the site that we selected because it had a variable terrain that we were interested in to understand the thermal conductivity, understanding how the slopes contribute and the shade from the slopes contribute to how the body absorbs energy from the sun. We were hoping that by putting a lander down safely somewhere in this region, we would be able to make some progress understanding that. And you know, looking at this, I'm seeing these sand dunes, or what looks like sand dunes to the untrained eye, which my eye is very untrained, because I look at things with a terrestrial frame of mind, not yet trained in cometary geology. And you have to ask yourself, how do you get sand dunes on a surface, on an airless body like this? What is the physics that caused this material to be laid down in that manner? And we will find out, I'm sure. Fortunately, the people, we had a lot of navigators studying this landing, and again, this would be a question for Jens when he comes next week, but they really did, by the time of the landing, have a chance to narrow the landing ellipse incredibly. They really got an accurate positioning and understood a lot more about where the lander was going to go, much better than the incredibly large landing ellipse that we started with. So this is the view of the orbiter from the lander. So long, Rosetta, from the lander Philae. We were delighted to see this because obviously it meant that Philae was working and the cameras were working. I'm not sure if it's appropriate to talk a little bit now about the midnight message I got right before the landing day, which was that we have problems. And the canister that was supposed to fire and hold the lander down, they weren't sure if it was pressurized properly. And then they weren't sure if maybe the problem was that it was just that the signal that tells them that it was pressurized was not being sent properly. So they sent a patch to try to fix that aspect of the software. And the patch didn't work. They didn't test it before they sent it. And so they said, here, we'll do another patch. So they sent the second patch. And then they asked if they could have an extra day and land the next day and have 24 extra hours to fix it. And evidently, the Director General of ESA said no. We got the President of France coming, and we got all these dignitaries, and you're going. Okay, this is hearsay. Okay, this is hearsay, but it's a great story. I love this story. And so here we are. This is the view now of the lander going down from the orbiter. And then here it is, the little dot, okay, approaching the target. And then this is the view of the landing site from the camera, from the lander camera. Okay, as we're approaching where it was supposed to touch down at first. Gravity pulling it down. Once we kicked it off the spacecraft, we had no control over where it was going to go. I don't know, but it's approximately 7 hours and it's approximately 22 kilometers, so that gives you whatever that is. That is the escape velocity, right. About a meter per second, exactly, right. And then this is, as I said, we got the location, the landing ellipse really shrank once our understanding of the shape and the gravity improved. And so we have a pretty good idea of exactly where it touched down. And this is another picture of the approach. And this is the picture just before touchdown. The boulder here in the upper right corner is about 5 meters in size. You would not want to hit that. It's interesting because it seems to be submerged in dust just a little bit. And you know, how deep is this material that it's going to land in? And I think we still don't have the answer to that question. Let's see. This is from the orbiter camera taken a few minutes after touchdown, and this is where they think the touchdown happened. And there's a pretty big hole there. I'll show that on the next slide. And they think that this is the shadow. They think this is the rebounding Philae, and this is the shadow of Philae. They think that is what is in this image. Oh, okay, so there it is. So this is a time sequence. And you can see Philae here and here. And the order is that it's going in this direction, time-wise, okay? And here is the landing site there before and after the touchdown. And then this is sometime later capturing Philae in its rebound. Okay? Now, we don't know exactly where Philae is located now, although last week they showed us some delightful photographs, about a half a dozen photographs where people have gone in and tried to find it and have seen this tripod-like figure and said, there it is, and they're all over the surface. I found it, and it's over here. Oh, no, I found it, it's over here. So we don't still know where it is, but there are some candidate sites. I think the interesting thing about this particular picture is the touchdown and the hole that is left behind. And again, some possibilities have been suggested that this is about 1 meter deep and about 4 meters in width, and that's about the size of the lander. And it may have sunk about 1/2 meter until the material compressed enough to send it out again. And then that hole might have continued to collapse with this very friable, but yet with a high compressible strength, crusty material that the comet might be made of. On the other hand, there's some data that suggests that it really is only a few millimeters of dust, and underneath is a much harder layer, and it's that harder layer just a few millimeters down that bounced the spacecraft out. Okay, and so somebody asked at one of the science meetings, is this layer stronger than a creme brulee? And I'm like, I don't even know how strong is a creme brulee, right? How would you describe the strength of a creme brulee? And so of course everybody's trying to Google what's the strength of, and so an ice cube from your freezer is about 70 megapascals, and a silicate rock is hundreds of megapascals. And a creme brulee is probably about 4 or 5 megapascals. So that's probably a good analogy for what the strength of this thing is. Snow, like unconsolidated snow, that if you scoop something up to make a snowball, is a few tenths of megapascals. And then if you compact it to make something that nobody would really want to be hit with, I'm not exactly sure how many megapascals that is, but that's going to be between 1 and 7, let's say, megapascals. So the question is, did we fall into this stuff and did we compress it enough to increase the strength to the point where the spacecraft bounced out? And does that tell us what the physics of this surface is? So this is, again, in my opinion, as lucky as we were to not bounce completely off the target, we collected enough information to really move the field forward quite a ways, in my opinion. So the landing spot is in the red over here, and we think that currently it's somewhere over here on the edge. There's a possibility that in its flight it may have hit the side of something. It's not beyond the realm of possibility. And then it came to rest in a crevasse or a ditch. The following morning, we were in the media room, right? And we're thinking, we got to chase somebody down. Those guys were up all night trying to figure out what happened. And fortunately, the lander PI came in to visit us, and he began to describe where the lander came to rest. And by that time, he had some of these fabulous pictures. And so one of the legs is up in the air, and the other 2 legs are one of the legs is firmly in the ditch. And we've got some incredible shots. So there's one here, one here. This is sort of widely been disseminated, and it's got what looks like a very hard surface. Yeah, okay, so I was going to talk about that next, but let's look at this for a second. What I think is fascinating is this one, which is very difficult to see in this image, and hopefully they will release better pictures of this particular one. The PI calls it the perihelion cliff. So it's like, if we're in a cave, this is the ledge that's covering us, okay? And you can see that it's lit by the sun on this edge, but a better picture has a pretty good piece of it all the way around. And it is one of the most fascinating pieces of geology I've ever seen, because it looks like what we used to do in these experiments, where you would lay this icy stuff down slowly. It would drift down like a snowflake, but without that much volume, and you'd build up in a process called sintering. You'd have this very friable, porous, loosely consolidated, and yet relatively strong stuff. And that's probably what this is. And if it's true, that is incredibly fascinating type of material. And then you can see that what we also have is some other, there's different kinds of morphologies here. In this, right, here's the foot, okay? There may or may not be some broken pieces there. That's still being analyzed. This is the picture from the panoramic camera on the lander. So it has 7 different slots all around, and it was able to fill all those slots with, a view. And because it's at this weird angle, it can see the perihelion cliff, which is the ledge that's over the top. Okay, and this is along the foot. And again, so possibly this part represents this sort of sintered stuff. And you can go Google experiments where they do this, where they create this material, and it's at all size scales, very, it's hard to describe, but it goes down to several different size scales, almost like a chaos regime. And then you have what looks somewhat different in terms of that it's almost like a crystalline, where they have those surfaces in a crystal. Here. So is this the primordial substrate of a comet? And I can tell you that the engineers would never have let us land in such a great spot, scientifically interesting, okay? And so by sheer dumb luck, we have landed in this incredibly fascinating, scientifically interesting place for which to study the original material of the comet, and perhaps watch as this begins to become active again as we get closer to the sun. Almost all the experiments were able to do their work and gather data. This is an experiment that was, I told you that the scientists wanted to get some of the original material in a laboratory and measure what it's made out of. So here's a couple of grains that were collected by one of the orbiter instruments. And they're starting to analyze what it's made of, including its isotopic composition and its charge. So this is just fascinating. And obviously, we hope to gather many more particles and many more, and be able to get a huge cross-section of what the composition is. I want to close by talking a little bit about the implications of some of these measurements. And I'm going to remind you, this is the Nice model, which is in 2006, some cometary scientists gathered in Nice, France, to decide on what the origin of the solar system was, and they could only agree on this rough outline, that the solar system nebula after collapse, and this is kind of the Kuiper belt, the purple stuff, and the yellow stuff is the sort of between Uranus and Jupiter is the debris of that, in that inner, not the inner solar system, but kind of the outer solar system, as the outer solar system was forming. And the forming outer solar system was relatively unstable, and so unstable that Uranus and Neptune changed places in their orbit. And that gravitational cataclysm was sufficient to clear out the debris that was in between. So you have this, this scattering event that takes place, and most of the yellow material is scattered to the Oort cloud and also may serve as the material that was in the late heavy bombardment. In other words, it may have also come forward into the inner solar system and may represent material that hit the moon, hit the Earth, hit Mercury, and so forth. So here's our scattering event when Uranus and Neptune changed places, but the Kuiper belt remained relatively unchanged by that event. So comets like our target, Churyumov-Gerasimenko, is a Kuiper belt object and represents some of the material from the deep outer solar system. And then Oort cloud comets represent actually material that was formed closer to the sun. So that is the Nice model. There's another more contemporary idea of what happened in the early solar system called the Grand Tack. And if you would like me to talk about that, I will. I don't have a cool video that shows how that works. But basically the idea is that Jupiter went all the way forward like a skiff, like some ship doing the America's Cup or something, and then tacked around and went all the way back out to the orbit of Jupiter again, which sounds pretty crazy. But the more we look at these extra solar systems, the more we see a giant planet that's very close to the orbit of Mercury, which, you know, it just happens over and over again. So it starts to be not so crazy, and that's now a more popular contemporary idea of what may have happened in the early solar system. So some of the lander experiments, one of the mass spectrometers was able to do what they call sniff. It basically got some of the ambient material. We would, of course, hope later on, if we're able to bring the lander back, to be able to get some of the original material, so they were going to try to dig into that material that where we've landed, put it into the ovens, make the ovens, deliver that material to each of the mass spectrometers, cook it up, and then do the analysis. But even getting some of the ambient material, we're able to get a lot of results, including organics, which is very exciting. The orbiter mass spectrometer has been able to get fantastic results, including a lot of organics. She laughingly says that the comet smells like a drunk with all of the organics that they've been able to measure. It smells like horse droppings because they've got a significant ammonia measurement, and with all the different sulfur species, it smells like rotten eggs. So she likes to talk about the smell. One of the measurements we're looking forward to making is the 17O to 18O ratio, because it used to be, before the Genesis measurement, which was a measurement of the sun, the solar wind grains, they used to think that with meteorites and the Earth and Moon, that the solar system was organized along this red line. And now they're thinking that with the Genesis material sort of fell along a different line that connects with the meteorites. And the thinking is that comets may have ratios that are more out here. And so there might be the correct continuum for how the solar system is organized chemically might be more along this line, and the outliers are the Earth and Moon. So we're looking forward to understanding more about this particular isotopic ratio. And then one of the important measurements that we want to make is the deuterium to hydrogen, the D to H ratio. It turns out that the Oort clouds, I talked about the Oort cloud and comets being scattered to the Oort cloud, and those comets, none of those comets have any, their water does not resemble terrestrial water at all in terms of its D to H ratio. But Hartley 2, which was our first measurement at a Kuiper belt comet, had a measurement that was almost exactly the same as Earth's terrestrial water, and so excitement began to build that maybe that's the answer as to where Earth's water came from. That the D to H ratio proves that comets from the Kuiper belt have carried and are the carriers of water to the Earth. So tomorrow we will have a result. So I'm not going to tell you what the answer is, what Rosetta measured. But we are measuring things like the D to H ratio, the noble gases, the molecular nitrogen. All of these are saying that the comet was probably formed in a very cold place. And we are looking forward to what we're going to learn about impact theories, origin and formation, and the evolution, and so forth with some of these measurements. And the orbiter mission continues. We will escort the comet around the sun. The comet, the region is going to get warmer. So we showed that with the the red here, which is a perihelion. The comet will be much more active. Even though it's a relatively weak comet, we are going to be observing all of its activity, and we ostensibly end out here in July 2016. Back out to 2AU. Hopefully, that's where we'd like to be at the end. So many people have asked me, what is the future of the lander? The lander is stuck in a crevasse right now, but it is on a hibernation sort of a budget. So that's like your cell phone in the red zone. It's not completely dead, but you can't really do anything with it. My teenage niece and nephew love to be in that zone. Aunt Claudia, what do you mean you have 20% power left? You could go all the way down to 1. So we're down there, okay, and we get about an hour and 20 minutes of sunlight per day. As we get closer to the sun, the actinic flux of the sunlight will increase, and we should be able to get more and more power into the solar cells. So they expect that by March we will be able to at least communicate with the lander, and that by June we will be able to maybe activate some of the experiments again. So that's kind of what we're looking forward to through the summer. I think that's the conclusion. Rosetta is an ESA mission with contributions from its member states and NASA. I just want to make sure to emphasize that it's not a NASA mission. And you can find more at the ESA blog and follow at ESA_Rosetta. And this is my final slide, which is a selfie of the comet with taken from the lander. That's it.
So now we've come back to the light. If you have any questions, put your hands up. I'll get around to you. Claudia, I've got the first question, though. You mentioned that as you get closer and closer into the comet, as the orbiter does, it's not able to carry out those the same orbits as you'd like.
Right.
So what's the state of the orbiter at the moment? Where in that trajectory is it, and how, why aren't you able to circularize the orbit as you?
It's a three-body problem, right? It's the presence of the other planets start to have more of an influence on the pull of the sun, and the other planets start to have more influence on the orbit. So you literally cannot do. There's not enough mass in the comet to have a regular orbit, a circular one. So you can hover. There's various different kinds of configurations you can do, but a bound orbit that's bound to the comet becomes impossible, and that will be just about mid-January 2015. So we will do lots of swoops and flybys, and we spend a lot of time arguing over what the altitude of the flyby is going to be now. So right now we're going from 30 kilometers to 20 kilometers. We'll do a bound orbit at 20 kilometers for 10 days, and then we'll go back up to 50 kilometers, and then I think we spend, I'm not sure how many days at 50 kilometers, and then we move to another configuration. So we actually have two different plans. We plan for high activity and regular activity, and we're constantly predicting the weather, because if activity picks up, we have to retreat away. So that's another one of the wrinkles of planning for this mission.
A very interesting talk. Looking at this picture, I would love to go to that comet, and I would like to go with a buddy. And one of the first things I would like to do is play a game of catch, maybe with a baseball standing on the head and the neck between the two of us, which leads me to my question. Throwing the ball is going to be influenced by the forces there. Gravitational stuff, and then maybe, I don't know if there's enough centrifugal force. Can you say anything about what the gravitational / centrifugal force field is, and what the trajectory of throwing a baseball would be on that little diamond?
I cannot.
Okay.
I cannot say anything about the gravity field, except that it's complicated. There's a well, obviously, where that neck is. So that might be one of the most interesting places to try to throw. But I would imagine you would have to also be anchored pretty good.
In the before and after pictures of the landing site, it looked like there were two spots
Right.
kind of close to each other.
Right.
Do you have any guess as to
Right.
why there's two spots?
Right. So I don't know how many people have told me that those are the three legs. Okay. But it's too big. Okay, it's too big. And so they think that one is actually the Philae in its rebound, and one is the shadow of the Philae. So it's part of it is the timing of when they took that picture was shortly after, the touchdown. And so they think that the big hole is a hole that was created by this impact, which was some 220 milliseconds in duration, and then it came out, and what you're seeing is Philae coming out and the shadow. Now, that understanding may change, as you know, right? They've had that data for 30 days or less than 30 days, and we met last week and we talked about it, and there was not agreement on exactly what that is. But the camera team's analysis is that that's what they think they see there.
What's the propulsion technology of the orbiter?
I'm sorry?
What
The
is
propulsion technology?
Yes.
Well, it's normal. It is, it's got the usual rockets and so forth, and propellant. So we have a lot of propellant to change the trajectory and to tweak it. Okay, so we brought a lot of propellant with us because we knew we were going to have to, like I said, retreat back from the comet when the activity got too much for the instruments, or if a jet suddenly went off, and then you're like batten down the hatches and pull back. So we've got more than the normal amount of propellant, but I can't tell you. You're going to have to save that question for Jens. What is the actual rocketry that was used for the orbiter propellant?
Claudia, that was a wonderful talk. And for the audience, they may not know that Claudia is giving a version of this, but it will be slightly different tomorrow at 10 o'clock at NASA Ames. And if any of you would like to go, I would be happy to get you a badge to get in there. Claudia, I'm wondering if you think the D to H ratio the embargo might be lifted before 10 o'clock tomorrow morning.
That's a really interesting, I will find out. Okay, that's a great question, okay?
I gather from what you said that there's no chance that the rotation of the comet will bring the lander into enough sunlight to do anything?
Yes, no, it will. Okay.
It will. Oh,
and it's
okay.
not going to be in the darkness. When we go into, it's in this northern hemisphere right now, when we get to perihelion, it will still be enough light where that crevasse is. It was really lucky. Okay. I mean, I don't know what those guys did to deserve that kind of luck. Okay. So we will have enough light to recharge the batteries and hopefully reactivate some of the experiments. Okay.
But that's not until
June. So between March and June is the time frame where we think we'll be able to get the batteries recharged, and then perihelion is in August. So it's a great time to be sniffing whatever's coming out of this crevasse. If the crevasse becomes active, what if we get blown out of the crevasse? I mean, everybody has all these scenarios, right, for what might happen. But we're looking forward to that, and I'll be honest, is the camera still rolling? Okay. Yeah, step off to the side. There's one experiment that I'm really hoping that we're able to get good data, and I think they need as much data as they can get to do the best job. And I think I mentioned it was my favorite lander experiment. That's the concert. So it's a really tough experiment to pull off. And I have the sneaking suspicion that they are going to need as much data as they can get to try to do a good job with that experiment. So if we can come back on and get both radio receivers going, we don't even have to turn the thing or have any other mechanical things going. But if we can get more data in that experiment, I think that would be very exciting.
And the comet's always been described as a dirty snowball.
Right.
Can you distinguish the material of the comet versus the vapor that is actually coming off with any of the instruments?
So the dirty snowball. I mean, I actually had a bunch of slides that I was going to use for the press conference that we hope to do next week at the AGU. And they told me to get rid of that dirty snowball. You know, I had Professor Whipple on with his desk with his dirt-covered ginormous snowball. And I love that shot, and it's so wrong. I mean, it's just so old school thinking in terms of what this is. First of all, I think we began to realize that an icy dust ball was probably a more accurate description of a comet. That you have this IDP style dusty refractory stuff in which the icy material is intimately mixed. And the question of how intimately mixed that stuff is still, I think, not answered. So is it fundamentally intimately mixed? You know, with Rosetta, we should be able to figure that out with these grains that we're measuring. I showed you 2 of the grains that they're measuring now. So, and then what are the vapors that are coming off? This is part of what the orbiter's mission for the next 15 months is going to be, is taking those measurements and getting a sense of what the composition, and then what are the parent gases and the daughter gases, and how much chemistry is going on in the coma region is also one of the things we really want to do.
Actually, 2 questions. One, there's a magnetic instrument on the lander. Did anything come out of that?
Yeah.
Okay.
Yeah, they were on the whole time, and it was the magnetometer that helped them learn that it was moving, and also learn when the touchdowns happened. And then there's an orbiter magnetometer as well, and there's a plasma instrument. So the ROMAP, which is the lander magnetometer and plasma instrument, was on the whole time. So they're reconstructing all the plasma sort of what their understanding of what happened in that region.
But is there an intrinsic field with the comet? Is this the solar magnetic field that's moderated in some way by the presence of the comet?
A part of it was the solar magnetic field. And I cannot tell you right now about the intrinsic magnetic field of the comet.
That would be
really
very
interesting
cool,
to know. Yeah.
And then the second question, if I may, is what are the noble gases?
Again, are we still taping?
Yes.
Okay. There's an interesting phenomena in science where you want to publish a paper with really interesting results, and then sometimes some journals, not all, don't want you to talk about what the results are before they're released to the public. So I would say I'll send you an email when those interesting results are made public.
Maybe Jens will be able to help us next week too.
But argon would so the interesting question is these are not, they don't recombine with other molecules. So when you measure them, they're telling you what the freezing temperature was. So you want to know as the comet's coming closer to the sun, you're watching very carefully to see are we seeing argon, neon, or xenon, and at what range do they start appearing, because that's going to tell you a little bit about what the original freezing temperature or formation temperature was. So yes, we're very interested in knowing the answer to that question.
That was my thesis.
Oh, is that right? Okay.
I know there are a lot more questions, but we're going to have to get people who have final questions to come up and talk to Claudia, and she probably will also have the camera turned off, so she might talk to you a little bit more about those results as well. But Claudia, we have here a special SETITalks mug. It's covered perhaps in something commentary like. It's very dark.
Yeah,
very
okay.
Dark
Oh, yeah.
so
there we go.
yeah.
Okay. With the...
Some robots on
some
there.
aliens.
Yes,
yeah.
yes,
Alien
some alien
life.
robots.
Okay.
That's right. I'm not sure how they play into Rosetta.
Okay. Well, I'll figure out a story. Okay. They're the white fluffy stuff.
Right.
Not quite though.
Please join me in thanking Claudia for a great
Thank you.